Hello everyone. Welcome to the last video of week 2. In the previous video, you learned the method of maximum likelihood to determine estimators for parameters of discrete distributions. In this video, we explain how this principle is used to determine such estimators for parameters of continuous distributions. Suppose we are given a dataset that is modeled as the realization of independent random variables with a model distribution that is characterized by a parameter theta. The method of maximum likelihood for a discrete model distribution was to maximize the likelihood L of theta given by the product of the marginal probabilities. Now, if the model distribution is continuous, then from probability theory, it follows that each of these marginal probabilities is equal to 0. So the likelihood becomes 0, and there is nothing left to maximize. Therefore, we have to think of something else. Well, let us start with the simple situation that we have one observation that is modeled as the realization of a continuous random variable with density f. For simplicity, suppose that f is characterized by a parameter theta, which can only take two values, say 0 and 1. Now suppose we are facing the following situation. So here we have the graphs of two possible densities, f0 and f1. And suppose that our observation x is at this position. Now, from probability theory, we know that the height of a probability density at x represents how likely it is that x will be generated from that density. So in this situation, it's more likely that x is generated from f1 than from f0. And so, if we need to choose between the two values for theta on the basis of this observation, we would choose theta equal to 1. Now suppose we have a data set that is modeled as the realization of independent random variables x1 to xn with the same density f. And suppose that f is characterized by a parameter theta. Now the previous example is a motivation to define the likelihood for the data set by L of theta equal to the product of the values f of x1 up to f of xn. A similar expression as in the discrete case, but now we have marginal densities instead of marginal probabilities. As before, the maximum likelihood estimate for theta is that value of theta for which the likelihood attains its maximum. And once again, maximization of the log likelihood is often easier than maximizing L itself. Let us illustrate things with the following example. We have a dataset that is modeled as the realization of independent random variables with a Pareto distribution with parameter alpha. So the role of theta is played here by alpha. And the density is given by the following formula. The likelihood is then equal to the following product. Now we want to find out for which alpha this expression is maximal. As in the previous video, we can make things easier by taking logarithms, but before doing so, let us first write the likelihood in a more compact form. We can merge all alpha terms and merge all x's to the power alpha plus 1. And this leads to the expression on the right-hand side. To determine the maximum, we first determine the log likelihood. And note that all the x's are greater than 1, so taking the log does not give any problems. Let us continue with the log likelihood. Now computing the derivative with respect to alpha and setting this equal to 0 gives the following equation. Now from this equation we can easily solve for alpha. As before, we must still check whether this is a maximum. Since the second derivative is strictly negative, we have a maximum. So we conclude that the maximum likelihood estimator for alpha is n divided by the log of the product of the x's. Now at this point it is interesting to see what the method of moments would give. From probability theory, we know that the first moment of the Pareto distribution is equal to alpha over alpha minus 1, but only for parameter values of alpha greater than 1. For values of alpha between 0 and 1, the method of moments cannot even be applied. For values of alpha greater than 1, the method of moments estimate is solved from this equation. This can be rewritten as follows, which then leads to the estimate x bar over x bar minus 1. So we conclude that the method of moment estimator can only be determined when alpha is greater than 1. And in that case, it will be different from the maximum likelihood estimator. Next, let us consider a slightly more complicated situation. Suppose we have a data set that is modeled as the realization of independent random variables with a normal distribution. The model distribution is characterized by two parameters, mu and sigma. So here the role of theta is played by the vector mu comma sigma. Now the density depends on mu and in sigma in this way. So in this case, the likelihood is a function of two parameters, mu and sigma, and is given by the following product of normal densities. Now at this point it becomes useful to use the sum notation from calculus. We briefly write the product as follows. Namely, the product of e powers can be written as e to the power sum of all exponents. And furthermore, we are merging the terms with pi and merging the terms with sigma squared. Now, the method of maximum likelihood is to determine for which pair mu and sigma this expression is maximal. As before, we first compute the log likelihood, which can be written as the following summation of three terms. Let us continue with this log likelihood. To determine for which pair mu and sigma this is maximal, we learned from calculus that we can set both partial derivatives equal to 0 and solve the resulting system of equations. Both partial derivatives are given by the following two formulas. Now you may pause the video here for a moment to check both expressions. But when we put them equal to 0, they lead to the following equation, system of equations. Again, you may pause the video here for a moment to check this. Let us continue with this system of equations. The first one is solved for mu equal to x bar. Inserting this in the second equation and then dividing both sides by n gives us the solution for sigma squared. We should check that whether this is a maximum. Now for calculus, we learned that this can be done by computing the matrix of second derivatives. But that goes a bit too far here. Well, it turns out that the solution found is indeed a maximum. So that means that the maximum likelihood estimators for the parameters mu and sigma of the normal distribution are given by these two expressions. As a final example, we return to the serial number example in the first video of this week. Estimating the German war production was simplified to drawing numbered balls without replacement from an urn containing balls numbered from 1 to k. In the third video of this week, you learned that the method of moments estimator is twice x bar minus 1. Well, let us find out what the maximum likelihood estimator is. Suppose we have drawn x1 to xn without replacement, then the likelihood is equal to the probability that this particular data set occurs. This is the probability that the number on the first ball is little xn, and on the second ball it is little x2, up to the number on the last ball is equal to little xn. Now, because the xi's are dependent, we cannot turn this into a product of marginal probabilities. But we can determine this joint probability. Because the balls are drawn with equal probability, the probability of each sample of size n is the same. Now, the number of ways you can draw n numbers from the numbers 1 to k is k choose n, which can be written also as this expression. The likelihood for our dataset is then simply 1 divided by this expression. Now note that this only holds if the number of balls in the urn is at least as large as the maximum number in our dataset. And otherwise, the likelihood is 0. Now, to find out for which k the likelihood is maximal, we draw the graph of the likelihood as a function of k. We mark the observations in our dataset on the horizontal axis. And now the likelihood is 0 for any k that is smaller than the largest observation. And from the largest observation to the right, it has the expression that we derived before. Now, it is clear from the graph of the likelihood that we cannot differentiate to find the maximum, since the graph is not even continuous. However, it's also clear from the graph where the likelihood attains its maximum, namely for k equal to the largest observation. And therefore, the maximum likelihood estimator is equal to the maximum of our data. Now, when we inflate this with n plus 1 over n and subtract 1, we find estimator 2 of the serial numbers example in the first video of this week. Well, up to this point, you have learned two general methods of estimation that arise from different principles. Maximum likelihood is based on the form of the distribution, whereas the method of moments is only based on the moments of the distribution. Now, it's not difficult to think of two different distributions with the same moments. For example, a standard exponential distribution has first two moments equal to 1 and 2. And on the other hand, a normal distribution with parameters mu and sigma both equal to 1 also has first two moments equal to 1 and 2. Now, the form of the distributions is completely different, but they have the same first two moments. And therefore, the form of the distribution provides more information than the corresponding moments. In view of this, it can be expected that the method of maximum likelihoods produces better estimators than the method of moments. And this was indeed illustrated in the serial number example in the third video of this week. The method of moment estimator T1 has a larger mean squared error than the largest order statistic, which is the maximum likelihood estimator. This brings us to the end of this video. Now, I invite you to do the exercises in which you can practice the method of maximum likelihood in a variety of estimation problems for continuous distributions. Next week, we continue with a new topic, testing hypotheses. See you then.